All right, so we have wrapped up talking about TCP, transport layer and TCP. There's just a few things that I want to add onto that, onto what we discussed last week, right? So last week on Thursday, we finished talking about congestion control, and then we talked about sort of questioning the end-to-end principle, right? Do you guys remember that? Okay, so I want to just do a few more things related to transport layer, but they're not in the notes. Okay, so they're I've handwritten them, and I'll upload these as supplementary notes to Luminous. Okay, but it might be a good idea for you to sort of take notes now as well. So I want to say a little bit about TCP throughput. So this is the analysis of the performance of TCP, right? We already hinted at it. So when we talk about throughput, we can have several notions of it, right? One notion is the idea of instantaneous throughput. What is the throughput now, right? So we call that the instantaneous throughput. And you can say, what is the average throughput? So the average is over some duration, let's say some long window, okay? Actually, it turns out instantaneous throughput is also an average. It's just that the window over which you average is much shorter. Okay? So in the end, all of these are roughly the same, except when we talk about average, we usually mean long-term average. So we might say over the duration of the entire flow. Okay? So if the flow is going to take 3-4 seconds, then it's the duration of the entire flow. Whereas instantaneous is more like, what am I getting right now? So it's over a smaller interval. You sort of take averages. And what we're really interested in is the number or the amount of information that's decoded at the receiver, right? So to turn it into a throughput or into a rate, right? It's the number of, let's say, information packets, or you can change your units. It can be bits, bytes, information packets, segments, right? You just have to be clear about what your units are and be consistent. Okay, so it's a number of, let's say, information packets decoded successfully at the receiver. Okay, that's really what you want to do. You want to talk about throughput, right? It's at the receiver. But remember, between the sender and the receiver is this complex network. So actually, trying to get an analytical handle on the throughput is challenging. All right. So for our analysis, we're going to start. We're going to assume we're using some flavor of TCP, right? I guess when I don't specify, I think it's okay for us to assume we are using TCP Reno. Okay, TCP Reno is the most popular, right? Remember, TCP Reno is the variant of TCP that treats triple duplicate X and timeouts in a different way. Okay, and so let's say we're assuming TCP Reno. So our congestion window, I'm going to call it CW, right? The congestion window, and let's say it's of size W. Right? Again, sometimes the units of congestion window are based on context. Right? They could be bytes, they could be segments. Okay, so you have to be clear based on the problem context what the units are. Right? Often I would tell you what I want the units to be in, so you got to keep that in mind. All right, so let's say we have a congestion window of size W. So remember, remember, congestion window is one of the constraints on the transmit window, on the sliding window that the transmitter is using to transmit, right? The sliding window is a number of packets that a sender can send unacknowledged, right? And remember, that transmit window is constrained by two things, right? What are the two constraints on it? One is the congestion window. What's the other constraint? The transmit window at the sender is constrained by two things, by two parameters. One is the congestion window that is computed by the sender as part of congestion control. What's the second one? So anyone want to hazard a guess? You want to try? Take a guess? No? Okay, the guy who just walked in, hi. We're talking about what constrains the transmit window, right? The transmitter has a sliding window. The size of it is constrained in two ways. One of the ways is the congestion control window. Do you know what the second constraint on it is? Like two things determine the transmit window. The congestion window and the, do you know? Yeah, what is that called? Yes, you're right. What do we have a name for it? The name doesn't matter, but you're correct. It's the buffer at the receiver. And how does the sender know that? Do you know how the sender knows that? Because the sender has to decide its transmit window. So how does the sender know that? No, how does the sender know the receiver, the free space in the receiver buffer? How does the sender know what the receiver is doing? It cannot, it has no information, right? Unless it's given information. How is it given information about the receiver? Yes. So where in the protocol? Yes, you're correct. So anyone? Yes, it's the advertised window field in the TCP header. And it's the flow window. We give that thing a name, the flow window. So the flow window, which is used for flow control, and the congestion window, which is for congestion control, are the two constraints on the transmit window. So the transmit window, the sliding window used for transmission, cannot be larger than either of these two. So it's the minimum of these two quantities. Okay? So we take a step back. We need to see the big picture, okay? Sometimes we get caught up in the, I call it, stuck in the weeds. But you need to take a step back and see the bigger picture. Okay, so anyway, so for this analysis of TCP, I'm going to assume a congestion window of size W. Sometimes this is called CWND. Actually, in the spec, in the protocol, it's called CWND. That's the variable name. Now here I wrote a W segment. So remember I told you the units of this are kind of up to you. Right? So here I'm saying it's W segments. Okay? Which means if I want to convert this to bytes, what do I have to do? If I want the congestion window in bytes, what do I have to do? Can you guess? I'm telling you the size is W segments, but I want it in bytes. So what do I need to know, and what do I need to do? Yeah. So what do I need to know? The number of? No. I said I want it to be in bytes. So what do I need to know? The number of bytes per segment. No, number of bytes per segment. You said bits. Right? You said bits. So you need to know the number of bytes per segment. And again, in the protocol, there's a name for it. We talked about it, right? What was that? Okay, we'll get to it in a second. So assume I have, assume no slow start. I'm just operating in AIMD. Remember, I told you that if you look at long traces of TCP, you will see that it's operating mostly in the AIMD phase. Okay, assume a round trip time is RTT. And then a segment size is MSS, bytes per segment. So remember, there was a variable called MSS, maximum segment size. So okay, so that's, I'm going to assume that bytes per segment. So now I know, right? How many, if I have a segment size, if I have W segments, then how many bytes are in the W segments? Yeah? Yeah, W times MSS. Okay, and so the question we want to answer is under these conditions, what is the average throughput of TCP? So I'm interested in the average now. So somewhat of a long-term average. Okay? And as I told you last time, we're going to compute something called the sending rate. Right? So the sending rate, meaning the rate at which the sender sends packets, bytes, segments, whatever, is an upper bound on the throughput. Throughput is measured at the receiver. But the sending rate is clearly an upper bound, right? Because you can't receive more than you send. Right? And we're going to compute this and use this as our first order approximation of the throughput. Right? If you want to actually compute the throughput at the receiver, you need to now take the network in between the sender and the receiver into account. Right? More precisely, you need to take losses into account and the retransmissions. Right? While it's not that difficult, it would take us some time. So what we're going to do is we're going to just use the sending rate as our first order approximation. Right? And it turns out this gets us the correct sort of trend and order of magnitudes that we need for this class. Okay? So the sending rate, if you remember, so this goes back to like stop and wait, right? So the way to look at sliding window. So I just want to know what is the standing rate of sliding window. If you sort of aren't able to get a handle on it, just think about stop and wait. Right? Stop and wait is sliding window with what window size? 1. Right? So, and what do you do in stop and wait? You send a packet, and then you wait. How long do you wait? Yeah? And how long does that take? The RTT. Right? Yeah, I mean, it's TP, but in talking about transport layer, we abstracted everything as round trip time, right? Yeah, so correct. So you have to wait 1 round trip time. Then, once that 1 round trip time is done, then can I send the second packet? So what's my sending rate? 1 packet every RTT, 1 over RTT, right? If in sliding window, I can send W packets unacknowledged. So what's my sending rate? W packets, I have to wait. Again, once I send W packets, I still have to wait for RTT. Here, assume that RTT is a bit longer than the amount of time it takes me to send W packets. Okay? In that case, what's the sending rate? Just W over RTT. W segments, so that's in segments per unit time. If I want to convert to bytes per unit time, it's just WMSS. Right? As long as RTT is expressed in seconds and the numerator is expressed in bytes, you get bytes per second. Okay, so this is WMSS over RTT, bytes per second. Okay, if you want the answer in segments per second, it's just W over RTT. Right? Or if you express W as bytes, it's just W over RTT. Okay? So I don't want you to memorize formulas. I want you to get the idea. Right? It's just how much you can send before you can send again. And you have to wait RTT. Right? Okay? So this is the sending rate, and this is going to be our first sort of first order approximation. We'll try to make this slightly better, but not much better. It's still the first order approximation, where we'll take into account some retransmissions. I'm not going to take into account the losses yet. Okay, that's the second order approximation. Okay, which we're not going to do. So remember, during AIMD, like when you're looking at this here, right? If I'm looking at this here, like you see that so every time I get a triple duplicate ACK, so remember I told you Reno, we're looking at TCP Reno, the window size gets cut in half, right? Right? The window size gets cut in half here. So kind of you can imagine what you're doing is you're kind of alternating between W and half W, right? So when I'm at W, my standing rate is this. When I'm at half W, what's my standing rate? Well, my congestion window is cut in half, so what's my standing rate? Half, right? So my standing rate is just half what it was before. right? So I'm just using S as my sending rate. So it's just half S. And since I'm kind of alternating between these two and I'm doing linear increase, what's the average? Yeah, it's just the average of 1 and 1/2, which is 3/4, right? So we get that that if I'm sort of alternating here back and forth, I get 3/4 of this W times MSS over RTT. So anyway, this is just a scaled version of the original one, right? So it just takes into account the fact that I have this sort of decrease in RTT, this linear increase and decrease. It's not taking into account the actual effect of the retransmissions, right? If you take that into account, you need to take the loss rate into account, right? Because your retransmissions are going to depend on the loss rate, right? And it turns out, again, so do you think that the loss rate will, like how, so can you guess? How will the throughput depend on the loss rate? So as my loss rate goes up, what do you think will happen to the throughput? Sorry? Yeah? Yeah, it will go down and vice versa. So it's inversely proportional. But it turns out it's not inversely proportional to the loss rate. It turns out there's a function of loss rate in the denominator, right? And there's a square root of loss rate. And to derive that takes a little bit of work. Okay, but anyway, for us, this would be good enough. Okay, so we're going to use essentially, to me, it doesn't matter which one you use, W by RTT or 3/4 W by RTT. They're essentially the same, just scaled versions of each other, right? In any case, it's to give you the right sort of trend, right? Okay, any questions on this? So I think we discussed this W by RTT kind of maybe qualitatively, right? So this is just nailing it down. So this is going to be our first order approximation for the throughput of TCP. Let's see how we can use this. Oh, it's back here. Okay, so I'm going to use this here when I talk about, as an example, talk about TCP over fast links. Okay, by fast link I mean that my link rate is very high. For example, I could have a gigabit per second link. Okay, so what I'm trying to convey here is that so like you might think, for example, if you have a very fast link, you know, a T1 line, right? If anybody knows about these connections, a T1 is very, very fast. You might think that, oh, that's enough. I'm going to get awesome performance. It turns out that's not the case. There are many, many factors that determine the throughput. And we saw that TCP, through its window size and round trip time, affects the throughput, right? So let's see what happens if we talk about TCP over fast links. Okay, so let's say I have a link capacity of 10 gigabits per second. Okay, I can convert that to bytes by dividing by 8, right? Because there's 8 bits in 1 byte. Okay, and so the link rate, meaning this is the outgoing link rate. So I have a router that connects to another router. Okay, and you can think of it as the data rate. The raw data rate on that link is 1.25 gigabytes per second. Okay, so it's a very fast link. Now I'm going to use TCP with a maximum segment size of 1500 bytes. Okay, so we'll try to get some actual numbers now. Okay, so let's say I have 1500 bytes. I have a round trip time of 100 milliseconds. Okay, and again, I'm going to convert that to seconds so I can, you know, get my units right. Actually, if you want to, you can leave it in milliseconds, and then you will automatically get a rate that's in kilobits or kilobytes. But for the purpose, let's just convert this to seconds. Okay, and I'll ask the question, what is the required window size to fully utilize this link. Right? So to fully utilize the link means my sending rate matches the link rate. The link rate here is 1.25 gigabits per second. All right? So we know that the sending rate is WMSS by RTT, right? So what I'm asking here is, what is W? Right? What is the window size to make the sending rate match the link rate for me to fully utilize the link? Okay, and this is just sort of simple computation. You just solve for W here, plug in the numbers, and you get over 80,000 segments. That means I need a window size of 80,000 segments. And can somebody convert that to bytes for me right now? So there's 1,500 bytes per segment. So what is it? Can somebody just help me do it? I want to write it down to show you the sort of how big this number is, and sort of, yeah. Can somebody write it down for me? Can somebody compute it for me? Remember, there's 1,500 bytes per segment, and I have 83,333 segments. So 124, sorry. Bytes. Is that correct? Right, so that's what? This is kilo mega, what is that? 124, or roughly 125 megabytes. Is that correct? Yeah, so the point is, I need a window size of 125 megabytes to fully use this great fractional T1 line that I bought. Is this possible? Like, can I actually use this great service that I maybe I'm paying like $1,000 a month for it? Can I use it? This little mini computation tells me I need a window size of 125 megabytes. That's very large. So do you think this is possible? Yes or no? What do you think? Is it possible? Yes, it is. There's nothing that says you can't do it. So it's theoretically possible. That's correct. But, is there a but? There's always a but.
But it's unrealistic.
It's unrealistic. Why?
Because usually with the window size of 135 megabytes is usually already larger than the amount of data required to transfer.
Like maybe, but let's say I have enough data. I have lots and lots of data to send. But you're on the right track. There's something else that constrains you. Yes, you also need to do that. Let's say I can do that. There's another constraint on the window size, which is why I spent that time at the beginning of class. Yeah? This is the congestion window. So it says that so this says that for TCP to work, right, the congestion window, this is the congestion window, but there's something else that also constrains you. So I think like both of you are getting, it's the flow control window, and if the flow control window is smaller than this, then your transmit window is going to be what? Can it ever get this high? No, right? So you cannot utilize your link. So you have to remember that. This is, like you might think, like we already saw an example of this when we talked about the bottleneck principle, right? The bottleneck link is your weakest link. If you have a chain of, if you have a multipath route, and you have a weak link in there with a very low rate, then that's going to constrain your overall rate, right? So that was one example, and this is another example here. Something else is constraining your rate. Even though you have a very fast rate, the parameters of the protocol that you're using can also constrain you. Okay? So just having a very fast, like, it's like this. Having a very fast car, so a good example is having a Lamborghini in Singapore. Right? There's like nowhere to drive it. Right? You don't have like an Autobahn or anything, right? Like I see that. Like I'm driving in my wonderful Toyota Corolla, and suddenly I hear this very loud sound, and yeah, like I told you, there was like once there was this yellow Lamborghini, like driving around town, and yeah, he revs his engine and he goes like 100 meters to the next light, and then I get to the next light. So yeah, it's like a fast link, but if you don't know how to use that link, that you cannot get the performance that you expect. All right, so just a sort of mini computation, but I hope that we're getting some concepts, right? Like I want you to really think about putting together everything we've learned and being able to sort of look at a problem and bring to bear all these different ideas. Okay, it's not about just, I learned this fact here and learned this fact here and keeping them separate. We try to bring things together. All right, so that was TCP over fast links. Let me see. Okay, the third thing I want to do, I have 5 slides. Okay, I want to talk a little bit about resource allocation. We discussed that TCP is fair and efficient, right? Remember we said AIMD gets you to the intersection of the fair line. So remember we had the curve, we had TCP connection 1 versus connection 2, and then we drew the fair line and the efficient line, and the intersection of that is where you want to operate, fair and efficient, and TCP, meaning AIMD, pushes you to that. So that's part of resource allocation. How do you allocate resources? So I want to take a step back and just explore how you should allocate resources. Remember, when I say words like optimal, they mean nothing unless you give them meaning. You say, what is a metric by which I measure optimality? So here we're going to look at different measures, different ways to measure optimality. So, okay, we'll do an example here. 3 users, okay? I have a 90 megabit per second link, all right? And so basically these 3 users are competing for this 90 megabit per second link. So the situation is the same as before. I have 3 users that intersect at a router. Okay, the router has an outgoing link of 90 megabit per second. And the question is, how do you allocate it? Right? Like we're going to just say, what's a good way of allocating? In fact, I'm going to ask the question, like, what's a fair allocation? Oh, one other thing. The 3 users have different requirements. So user 1 wants 50 megabit per second. User 2 wants 50 megabit per second. User 3 only wants 10 megabits per second. So that's the requirement of the 3 users. Okay, I have a 90 megabit per second link, 3 users with these requirements. And the question is, what's a fair allocation? So can you think? What? Okay, so yeah, so I mean, don't worry about the it depends. I think we've beat it depends to death, right? So I won't say it anymore because you understand, I hope. But yeah, so tell me your name. No, what's your name? Spell it. Aryam. Okay, so Aryam thinks that what's fair is to give everybody 30, right? 30, 30, 30. Okay, I think that's a fair thing to say. Okay, so that's one thing. So anyone else want to either enthusiastically agree with Aryam or come up with another notion of fair allocation? Okay, so how? I can't meet their request, right? Because 50 plus 50 plus 10 is more than 90. So what can I do? Proportional. So you're saying that the total request is 110, correct? So I give everybody, yeah, so U1 gets 50 over 110, 2 gets 50 over 110, and 3 gets 10 over 110. So I think both of these seem reasonable, right? Yours is equal allocation. Yours is proportional allocation. Okay, can anybody think of either enthusiastically agree with these two? What's your name? Huh? Alan. A-L-A-N? Okay, Alan. So Aryam and Alan, both A's. Hopefully you get A's in the class. Okay. Aryam and Alan, anybody want to either agree with them enthusiastically or say, give a different one, yeah? 40, 40, 10. So that's interesting. How did you come up with that?
Since user 3 only makes 10 and not anymore,
Yeah.
so we can divide equally like 90 minus 10, 80.
Yeah. So what do you, yeah, but how did you come up with that? So this is good. So this is a third allocation. I like it. The allocation is 40, 40, 10, but I want to give it a principle. Let's see if we can find a principle. Because for Aryam and Alan's solution, we found a principle, right? Equal and proportional. I like your idea a lot. Can we try to find a principle? And what's your name? Oh, not A, right? Okay. Anyone want to try to follow up on what Ricky said?
The maximum you can give based on the user needs.
Maximum you can give based on the user needs. I like that, yeah. So anyone else want to add to that? In fact, I am kind of impressed with you guys. You came up with my 3 solutions. It's never happened before. Yeah, so this is, so your 40, 40, 10, like if I build on what you guys are talking about, it's kind of like, you can think of it as so the equal allocation is just saying I want everything to be equal. Proportional fair is based on what you ask for. I give you a fraction of what you ask for. And both seem nice. This is like, can I maximize happiness? Right? It's almost like it's a maximize happiness way of allocating. Because if you give 10, user 3 10, you've made user 3 happy. And then you make the other 2 as happy as you can. With the premise being, the closer you get to what you want, the happier you are. Right? Like, everyone wants an A. The closer you get to an A, the happier you are, right? So the closer that, yeah, so, and in technical terms, this is called the max-min solution. You're going to maximize the minimum that anybody gets. Okay? So yeah, like I'll show you. You actually figured out exactly what I did. Right? I'm very impressed. It's never happened before. Thank you so much. Right? So equal, proportional, and max-min. And these are sort of very common ways of doing resource allocation. Okay? Probably max-min is the one that you probably haven't seen before. Right? Have you seen this before? Or you were just looking at it and thought this would be good? Yeah. Yeah, it turns out that a lot of engineering problems end up being max-min. Now, if everybody wants the same, max-min gets to equal. Right? It tends to equalize. Right? But the nice thing is that if somebody wants less, so the max-min solution is also something like water filling. Like imagine you have cups of different sizes and you have to fill them. So the requests of the users are different cup sizes. So you fill everybody's cup as much as you can. User 3's cup, you're not going to overflow. That's a waste. Right? So you're going to fill it, and then you're going to take the rest of you're going to fill it to 10, and the rest of it you'll fill equally. Okay? All right? And it turns out that it's kind of what I
what we discussed before, that fair, efficient, good, optimal, best really don't have any meaning until you give them meaning. And you have to give them meaning by saying, what is my metric? Right? If somebody comes along and says, I require that everybody gets equal, that it doesn't matter if maximum is better from another metric. The equal is the best solution for the requirement that everybody is as close to the same as possible. Right? And so on. And proportionally fair is just another constraint that you could put on the problem. Okay? And a maximum is a little bit hard to understand, which is why I tried to come up with another way of looking at it: maximize happiness. Right? When you want to maximize happiness, like there's a travel site called Hipmunk. So who knows about it? HIPMUNK. And like you might think, I don't need another travel site, but they do something very interesting. They take flights, the duration and the price, and they try to combine it in such a way that they want to minimize agony. Right? Like for example, you might have, like the cheapest flight may have a huge layover. It may take you like 40 hours to get to your destination. Right? But if you add allow a little bit more, you can get a 20-hour flight. Right? So they're also trying to say, their solution is also not any of the standard, minimum price or minimum travel time or so on. It's a combination. Right? In the same way, max-min is sort of a combination. Okay? Yeah.
So what if, say, I got 3 clients. So the first 2 clients, say, needs 100.
Yeah.
And the last one needs 89.
Yeah.
Then we only have 90.
Yeah.
So then we give, with the max min, we give 89, the full 89. But then the first 2 only gets.
No. Sorry. I apologize. You don't give to the one user first. So this is a good question. The question was, let me not repeat the question. Let me describe max-min again. Okay, I think maybe something got lost in translation. So with the cup example, right? What you do is you don't, so I was wrong. You don't fill the third user first. You fill everybody, but you stop when the third user is full. So you give everybody 10, 10, 10. But then you stop because the third user is full. So you stop giving to the third user and you continue filling the other 2. Yeah, so if we had 100, 189, what we would do is we start filling everybody. And where would it end? Because I only have 90 Mbps, right? So I'm filling everybody, and you get 30, 30, 30. Yeah, that will be the max-min solution. Yeah. But if you notice, the proportional fair solution would be different. The equal gain would be the same. Yeah, I think there was some confusion in what I said. So is it clear now? Okay. Okay, so I think that's so. I just want you to think about resource allocation, right? Because TCP is fair. TCP will give you 3 TCP flows at an intermediate router. TCP will give you 30, 30, 30. Right? Assuming I don't put a constraint on my window size. I don't bound it. Right? If I allow the window size to grow, then we're exactly in this situation. Everybody wants a lot, but my pie is this big. TCP will output the equal solution. But it will do it in a distributed way. That's the nice thing about TCP, right? It's an algorithm that you have 3 non-cooperating hosts, like senders, and the distributed solution converges to the equal gain solution. I mean, the equal allocation. Okay? So sometimes you might read if you read a paper or something, you might read TCP fair. So yeah, TCP fair is this. The distributed hosts are running TCP. You can't do equal gain because there's no centralized controller. But TCP fair is the distributed solution that comes to this. Okay, everybody good? Any questions? Okay. Okay. The last thing I want to do is maybe just review the dynamics of TCP, right? We saw that diagram. You remember that diagram where you had slow start, then timeout, AIMD, and timeout, right? So we discussed TCP at that level, right? And we discussed all the mechanisms there. Just once, let's just go into what happens at every transmission. Okay, so we make sure that we understand. Okay, so TCP with slow start and AIMD. When we did the solution for, meaning the analysis of AIMD and the performance of TCP, we ignored slow start, right? Because as I said, the long range average performance doesn't depend on slow start. But I want to make sure we understand because slow start is part of TCP. We have to make sure we understand it. Okay, so this is Reno with slow start and AIMD. And the question is this. So I want you to try to work this out. Okay, so this is kind of like problem solving in class. So let's say I'm doing slow start, and I start with a congestion window of 2 MSS. Now, in class, we often said that the starting point is 1 MSS. But I'm telling you here that the starting point is 2 MSS. So I don't think you don't have to be thrown by thrown by that. I'm telling you the starting point. Okay, so I start at 2 MSS. This is my window size. Okay, now SS thresh is the window size to which I'm going to use slow start to get to. And then from that point, I'm going to transition to AIMD. Right? Remember, so slow start threshold, you can think of it this way. When you first start a connection, right, you slow start until you break the network, meaning you get a timeout, right? So I get a timeout, and now I sort of know that at this point in time, this is the boundary of congestion. I want to operate below this. So what I do is the reaction to the timeout is to drop the window size to 1, and then slow start to somewhere. To where? To half the point where you broke the network. So if I broke the network somewhere, I'm going to set this SS thresh to be half that value. Okay? So anytime I get a timeout, the window size where I got the timeout, I'll remember half of that value as slow start threshold. And the next slow start will slow start to this point. Okay, so let's say the slow start threshold is 8. Okay, slow start will start at 2 MSS. So I've gone my initial slow start. I get a timeout. And I'm telling you the slow start threshold is now 8, and my starting point is 2. So instead of dropping to 1, I'm going to drop to 2. Okay? So I did this to show you that nothing is written in stone, right? That dropping to 1 is not written in stone. You can drop to anything you want. Okay, but you don't want to drop to something too high, obviously. Okay, so the question is, now if I get a timeout on the 5th transmission, okay, what is the congestion window size after the 10th transmission? So you understand the question? Okay, so I'm at 2. Right, I've just got a timeout. I'm at 2, and I'm going to, my slow start threshold is 8. Okay, I'm going to slow start up to try to get to 8, and I get a timeout after the 5th transmission. And I want to know, then the protocol will continue on. I will get to the 10th transmission. I want to know what is the congestion window after the 10th transmission. So the way you probably want to do this is just, let me see. Just kind of do something like this. Like just write out what all the transmissions are and what the window size is. So for example, we know that transmission 1, I'm starting off at window size 2. So at transmission 1, the window size is 2. Then what's going to happen? At transmission 2, what's the window size? So what's the window size at transmission 2? Sorry? Yeah, because I'm in slow start. So it's 4, right? Okay. And at transmission 3? 8, correct. So now I've gotten to my SS thresh. So what am I going to do now? Yeah, I'm going to go into AIMD, right? So in transmission 4, what's my window size? Okay. And transmission 5? 10. But then what happens? There's a timeout. Okay, so what's going to happen? So what's going to happen now? Yeah, I think you're right. I want to make sure everybody's with me. So what's going to happen? Oh, sorry. Okay, so I just want to make sure everybody is with me here. Let me. Okay, so with transmission 1, we start at 2. So 2, 4, 8. Because I'm in slow start. In slow start, the window size increases exponentially. It doubles every round trip time. Okay, so 2, 4, 8. Then in transmission 4, I go to AIMD, which is linear increase. And here, we're just adding 1 every round trip time. So 8 plus 1 is 9, plus 1 is 10. And I told you at the 5th transmission, there's a packet drop. There's a timeout. So what happens in Reno when there's a timeout? So what's going to happen? Like you said half, right?
I said 2.
Oh, you said 2, okay. Anyone say half? The timeout. How does TCP Reno deal with timeouts? Yeah, it is. Yeah, so I'm going to go to 2. Correct. No, I didn't say you were wrong. I want to make sure everybody's with me. This is not about, I told you, I want you to do it. Sit there and do it. It's not about me presenting you. So sit down and do it. So you can finish this now. Tell me what the after the 10th transmission, what's the window size? So what is it? What's the window size? So what happens next? Next is 10. So at transmission 7, what's the window size? What is it? 4. Okay, yeah, because I'm doubling. Then transmission 8. Why? Why is it 8? Okay. What's your name? Sean. So Sean and tell me your name. Oh, Chen Hui. Sean and Chen Hui both say 8. That in the 8th transmission, the window size is 8. So who agrees with Sean and Chen Hui? Aryam, do you agree? The two A's, Aryam and Alan. Do you guys agree? Should be 8? What? Yes? How about you? No? Okay, good. We have a disagreeer. I like that. So, what do you guys think? At transmission 8. Okay, so we gotten to this point here. We said that transmission, we are here, right? So we're trying to wonder what is the window size at transmission 8? So did you figure out if you agree or disagree with Sean and Chen Hui? Okay. What are the rest of you? Come on in, join the club. Huh? Am I revealing the answer? It's okay. It's not. Why, you can like see through paper?
No, threshold.
Oh, yeah. Yeah, there you go. You're right. That means I revealed the answer before,
Yeah.
actually. So what happens when you break the network? What are you supposed to do? Like, what's the whole point? Like, so that's what I say. It's not about memorizing this. This probing mechanism, right? Remember, TCP is probing the network. What is it doing? It's pushing data into the network until you break the network. And then you want to remember that, right? Because the network is dynamic. Where you broke it, where it breaks changes as a function of time. So you need to remember that. The way we remember it is by, and I think I think one of your classmates said to me, like, why don't we try to like operate about like halfway down? Like, was that you? The Hebei, right? Didn't you ask me that? Yeah. So that's the whole point. You want where you operate is a function of where you broke the network, and I just got a timeout, right? That's breaking the network. So I have to know where I broke it, and where you broke it is encoded into where I'm going to operate next. I'm going to operate at half of where I broke it. So I broke it at congestion window 10 in the 5th transmission. So now I want to operate at around 5. So I go 2, 4. I'm not going to go to 8 because 8 is above 5. So in this case, it's a little bit tricky. You might wonder, oh, yeah, but you don't want to go above where the threshold that you set. So if you have to operate below it, you operate below it. Some people argue that, oh, maybe you should just make it go to 5. Instead of 4, 8, 4, 5. This is depending on how you specify your protocol. Okay? I'm going to just take the view that we're going to just not go above, right? So at this point, I'll stop a slow start and go into AIMD. Which then, what's the next? What then? Can you fill it in now? So at transmission 8, it'll be 5, 6, and 7. Okay? Okay, so that's sort of the, very gory, writing it all down. Is this what you were thinking too? The slow start threshold is not 8 anymore, right? It has to change. Okay? Okay, so sort of very, yeah.
So the slow start itself will not ever go to 5. It can only go to 4, 8.
Yeah, I mean, so as I said, this is like some, this is maybe a 3rd or 4th order detail, right? But I think, yeah, I mean, in this case, it happens that I'm 1 before, instead of going, the AIMD will get to 5. So whether slow starts get to 5 or AIMD gets to 5 is semantics, right? Yeah, to me, I think maybe the way I would interpret it is that slow start won't get above the threshold. Yeah, I think that's reasonable. I think TCP still works with that. If transmission 7 is what? Uh-huh. Remember, so you're doubling, right? So 3 should go to 6. But it's above 5, so you won't get to 6, yeah.
So we'll switch to AIMD, which means it's addicted, which means
Before, yeah.
so it's not directly using the threshold once it's above.
Yeah, correct. Yeah. Yeah, so that's what I'm saying. Let's agree that that's the behavior we'll have our TCP follow. Okay? I'm not saying that you can't rewrite the spec to do something else, which is once you get close to the threshold, on the next step, just clip to the threshold. You could do that. That will work too. Right? So in your example, Chanhui, you go from 3 to 5. Right? That will work too. Yeah. Okay? But in the spirit of being conservative, remember, this whole point is that, the reason that we drop to 2 or 1, and the reason that we cut in half is that, and the reason we do linear increase is to be conservative. Right? So in the spirit of being conservative, I want to never go above. Okay? It's not like a hard and fast rule. It's like there's a principle behind TCP. Be conservative when you're increasing. So keeping in line with that principle, we won't go above the threshold. Any other questions? Wait, oh, sorry.
After we have a condition window 2, then it times out. Then it become 1.
Oh, no, I mean, it depends. In here, I just set what happens when I get a timeout behavior to setting the congestion window to 2. If you get a timeout again, you stay at 2. You can't really go, I mean, it depends, right? If you specify I can go to 1, you go to 1. You can ask us the same question for you. What happens if you get timeout at congestion window 1? Right? You just stay at 1. Like you basically go home because the network is completely like, yeah.
Can the threshold ever be raised if the network changes, so you wanted to have a higher threshold number?
Yeah, absolutely. The threshold is just where you slow start to. The next time when you're in AIMD, your AI could get you very high. Then the next time out, your threshold is high. Yeah, so it's adapting. This SS threshold is only used once on the next slow start to get you quickly to where you want to operate. Yeah. Okay, thank you for the questions. Anybody else have a question? Okay, so we'll do one more thing. This was the 4th slide. The last thing I want to do is I promised you we are going to talk about why we have retransmissions at both layers. So I prepared a handout on the 3 why questions. I'll upload this to Luminous once we cover all 3. So we've already covered, if you remember, we've already covered the why MAC and IP addresses. So that's on here. Okay, I'm not going to cover that now. I'll cover the second one, which is why we have retransmissions at both layers, right? So I think last time I gave you a couple of questions to think about, correct? Did we start asking the questions here or not? Yeah, so remember, just like the MAC and IP addresses where we asked a series of questions to try to learn about what's going on, I want to do the same thing here. We'll ask a series of questions, okay? So the first question we're going to ask, because it's a choice between 2 things, retransmissions at both layer 2 and layer 4. So the first question is, what is the difference in the reliability at the 2 layers? So anybody can help me? What's the difference, right? If they were the same, they were exact, I could just drop it. So what's the difference? Yeah, so somebody said end-to-end reliability. Okay, so that's part of it. Yeah, so what's the difference?
On the transport layer is from like 2
Yeah.
different end-to-end users, but on the link layer is between 1 link.
Yeah, so transport layer is end-to-end between the sender and the receiver through many hops. The link layer is hop by hop. It's between one node and the next node in the route. Okay? So what we say is that the scope, SCOPE, the scope of the reliability is different. Okay? So the difference between end-to-end and hop by hop is scope. Like what you can see. Right? Scope is about what you can see, right? Telescope, right? Microscope. So scope is about what you can see. So the scope is different. Okay? So we see what the difference is, right? So transport layer, the scope is end-to-end, and link layer is point-to-point, or sometimes called hop by hop. Okay, so while the mechanisms may be the same, the scope is markedly different, is very different, which makes them completely different. So the question of why we have both is a good question. Okay, because it's two different things trying to serve the same purpose, And so it's a good question to ask why. All right, the next question I want to ask you is this. What kind of reliability do we actually want? Right, meaning, so you're correct, Chen-Hui. So the question is, in the communication problem, so we have this communication problem where you have a sender wanting to send to a destination through many hops. That's the problem. So in this problem, forget about what we do, what do we actually want? So do we want end-to-end or hop by hop? So this, in the last row, hi. What do we actually want? Sorry? Why? Yeah, correct. I mean, what I'm hearing from all of you, and what's your name? Huh? Sandhya. She expressed it well. When you send something, you want to make sure that the destination that you intended to send it to gets it, right? Right? When you mail a letter, you want it to get to the addressee, right? When you send an email, you want it to get to where you said to who, right? Okay, so you want end-to-end. Okay, you don't care really about hop by hop. You really want end-to-end. So I think that's my next point. Right? So we really care about end-to-end reliability. And since transport layer provides end-to-end reliability, it's good enough, right? So, you know, so if we drop link layer and kept transport layer, we'd be okay. We'd get what we want. You get the difference, right? I mean, sorry. You see the consequence of wanting end-to-end. Transport layer actually does what we want. So now the question is link layer good enough? So transport layer is good enough. The question is link layer good enough? I think that's my next question. I hope. Oh, sorry. But you probably guessed the answer already. But again, the answer doesn't matter. Why matters, right? So let's ask the question. Transport layer is good enough. Is link layer good enough? And I mean, don't you shake your head. I want to know why. So fine. The answer is no, but why? Why is link layer not good enough?
Because it is a between end-to-end, it's just online.
Okay.
Because we only know if we go from node A to node B, say we want to send from A to C, we only know that it goes to B, but we're not sure that B will send it to C.
Okay, so let's do this. Let's create a route. Okay, I'm going to have to pick people. There's some people I know, so Chen-Hui. Let's see, but I need to go far from you. I can't keep doing What's your name? The guy in the red shirt, yeah. Spell it? Vinit. So, Chen-Hui, Vinit. And let's pick somebody I don't know. How about somebody in the back row? The guy in the green shirt. Hello? He's too busy. Hi. What's your name? Thomas, right? Okay. So Thomas, you're going to be my destination. I'm creating a route. Okay, I'm the sender. You're the destination. Chen-Hui, Vinit, Thomas. Okay? So now what link layer does is make sure my packet gets to Chen-Hui. Then Chen-Hui's link layer makes sure the packet gets to Vinit. And Vinit's link layer makes sure the packet gets to Thomas. So why don't I have end-to-end? So I have 1, 2, 3 reliable links. Why is it 3 reliable links stitched together don't give me the confidence that my packet got to Thomas? So, like you were saying something, but does this confuse you a bit? If yes, I'm happy. No, I'm just kidding. But I mean, this is the question, right? Instead of thinking abstractly, we make it very concrete. Why is these 3 reliable links not guarantee me, the sender, my packet got to Thomas? That's the question. Is link layer reliability good enough to give me what I want, which is end-to-end? Why? You say no. Tell me why. So, yeah, I know, but that's like an abstract argument. I just said my packet is guaranteed to get to Chunhui. Chunhui's packet is guaranteed to get to Vineet. And Vineet's packet is guaranteed to get to Thomas. Oh, my packet becomes her, right? It become her packets. In some sense, that's how it's supposed to work, right? That's how the multi-hop works, right? Do we? Okay. So the retransmission might screw up. No, it won't. The link layer will guarantee it won't screw up. Okay, I want you to expand on that. Okay. So, yeah, I mean, you're on the right track. Good, thank you. That's thinking out of the box. So you said I told you that already? Kind of. So then.
No, but in this example, for instance, like some node and then we just power off.
Yeah. So if I told you, I want to hear you. If you understood what I told you, you should be just telling me the answer and we can move on. Yes, that's what I'm saying. Getting the answer is not good enough. You need to understand the concept. So if I ask you the same thing slightly differently, you're not like, huh? That's a brand new problem. Right? So I think you're on the right track. So I'm glad you made the connection. That's good. So, everyone else, why is, actually this is a very important, the answer to the question depends on this. Link layer is not good enough. So you need transport layer, right? So why is a series of reliable links not enough? Can you tell me?
Because of, like, I think what he says is that the node is not reliable.
Yeah.
In the sense that when you send the data to Chunhui, Chunhui might have some error and retransmit the error to somebody else.
No, you see, like that's not correct.
Right.
Because the link layer guarantee. So that's my point. Link layer is a reliable link. There's no error there.
Yeah, but the node itself could manifest some error and retransmit that error reliably to another node.
I see. Yeah. You're right. Yeah, exactly. Yeah. So the point is, the link layer guarantees my packet will get into the buffer of the next hop node. It does not guarantee that the next hop node will transmit the packet. That's the difference. Maybe that's what you were trying to say, but we need to learn to say it very precisely, right? I know that's what you were trying to say, but we're engineers, right? We're going to graduate from NUS as engineers. All of you are going to graduate, so you need to represent that, okay? So this is good. I'm glad the ideas are there. Let's make the manifestation of the ideas precise, okay? So the point is, again, to repeat, the link layer is not good enough. Is not good enough because it only guarantees that it gets into the buffer of the next hop node. It does not guarantee the next hop node will forward the packet. So, for example, the next hop node could run out of power, and I like your idea that they could have some errors there that in the circuitry and the hardware and memory, right? And then it's going to transmit those errors reliably. That's a good way of looking at it. I'm going to use your example from now on because I didn't think about that, but that's exactly what I'm trying to say, right? And so that's why you cannot build an end-to-end reliable network with just link layer. So link layer is not good enough. Then the question is very intriguing. Why does the current internet stack, why does the TCP/IP stack have both link layer and transport layer reliability? right? This sequence of answers is slightly different from MAC and IP, right? MAC and IP, we saw that both are good enough, right? And both were good enough, but one was preferred, IP was preferred, and we used both for like an engineering for efficiency reason. Okay? Here, both are not good enough. Only one is good enough. Link layer is not good enough, but we still ask the question, why do we use this other mechanism? And there's no hiding. I mean, it's the same reason as MAC and IP. It's for efficiency. But can somebody explain why? You want faster correction once there is an error. No. Somebody's, hang on. Yeah? Can you speak a bit louder? I can't hear you. Oh, undersea cables? No. You do go through undersea cables for the long hauls, but for this point, we don't need to get to that level of detail. And it's not about errors. If you think it's about errors, then you're saying that link layer is not really reliable. Then you just said you don't want to recover until you get to the endpoint. Link layer is reliable.
Yeah, it is, but it will take longer time.
Why?
Because you need to go through all the nodes.
You have to go through all the nodes anyway.
Yes, but if you only correct once at the other end, then you have to maybe like send another acknowledge or some message to the sender initially to correct. But if each node ensures it, then every kind of insurance is much shorter time, so it links up to faster.
Yeah, okay, I see. Okay, so your example is good. I like it. Let's do a slightly easier to understand example first, and then I'll talk about what you said, Chen-Hui. So let's say that there's this like path me, Chen-Hui, Vineet, Thomas, right? But suppose it's longer. It's like 20 hops, okay? And so let's say like between Chen-Hui and Vineet, there's like 18 hops. So 1 hop, then 18 hops, and then to Thomas, okay? Now, suppose that the packet makes it all the way to Vineet, okay? It gets to Vineet. But it gets dropped on the last hop. Something bad happens. Then what has to happen if I just have end-to-end? Yeah, there'll be a timeout at the sender, and TCP will kick in, right? And I'm going to have to resend from here, right? And I'm going to go through all these 18 hops again. So that means the very first time I used all these resources, and it's all wasted, because on the last hop it got dropped. So I'm giving an extreme example. And it would be nice, and this is how it connects to what you're saying, it would be nice if you could recover locally. So when some packet gets dropped at Vineet's side and Thomas doesn't give an ACK, Vineet has a link layer mechanism to make sure that that packet gets to Thomas. Right? So you get faster recovery. You don't have to wait, because we already know transport layer is good enough. You can wait for the timeout, TCP to kick in, and I'll retransmit. But for efficiency reasons, we put in a local recovery mechanism. And the same idea applies to what Chen-Hui said, that instead of a packet being dropped, suppose a packet is an error, right? You can recover locally. I think that's what you were trying to say. So thank you. I think I missed that. So you're exactly right. Okay, so we do it for efficiency reasons, okay? So I think that's my last line here. Link layer retransmissions are there to make failure recovery faster and more efficient, right? So the overall delay is less because we have a local recovery mechanism. But you don't do local retransmissions forever. Like for example, Wi-Fi, when you are, there's a link layer recovery as well, but you transmit like 10 times at most. You got to look at the protocol exactly, but it's about you transmit 10 times. If it doesn't work, you drop the packet. Right? That means you force the host to find a new route, essentially, because this route is no good. Right? Okay, so we've answered the second why question. Okay, the third why question that you can start thinking about is why are there checksums at layer 2, layer 3, and layer 4? So this bugged me for a long time, and I'm not even sure I have a good answer yet. But you notice there's a checksum at layer 2, meaning a CRC check, and CRC is an error detecting code. It's a channel code, it's redundancy added to do error detection. That mechanism exists at layer 2, layer 3, and layer 4. And then on top of it, application layer has error recovery mechanisms as well. That's not even listed here. But if you just ask for these 3 layers, why is it there? So, okay, it's something that's the third why question. All right, let's do this. So I'm done. With this, we're really done with TCP. The next topic is network layer. Any questions? We'll take a short break, and then I want to start network layer. Okay, so let's take maybe a 5-minute break. When we come back, I'll start the network layer. Okay, thanks. So let's come back in 5 minutes. Okay, so we'll talk about network layer now. This is the sort of the second major topic. Okay, remember the function of network layer, right? In the sort of everyday language where we're trying to do the function of every layer, the job of the network layer is to find a set of reliable links from source to destination, right? Where the link layer has made all the links reliable, the physical layer has made the link, created a link. Network layer makes the link reliable. So now we have a set of reliable links all through the network, and the network layer stitches together a bunch of reliable links to connect source to destination. Okay? And then the transport layer sits above that and uses this set of reliable links, which is called a route, to to create end-to-end reliability, to make sure that when you send packets over this route, it gets from sender to destination. Okay, so network layer is about finding the set of reliable links here, and that the sort of function that we all think of when we think about network layer is called routing. Okay, there's actually 2 main functions that a router has: forwarding and routing. Okay, we're going to take a look inside a router. We'll look at routing algorithms, and we'll see how this plays out in algorithms like in networks like the internet. Okay, so that's our aim in talking about the network layer. Okay, so let me see. Yeah, it's okay. I have this. Okay, so just like we saw for all the other layers, each layer basically forms a virtual connection between that layer at different nodes, right? Because if you think back to the encapsulation idea, so at the sender, information starts at the application layer, and it comes down the stack. And as it comes down the stack through the different layers, each layer adds a header and or a footer. For example, link layer adds a footer, right? The information that's in the header and the footer is intended for the layer, is to help the layer carry out its function. Okay, so as I'm going down the stack, the payload is being wrapped around by the headers of the different layers, and then it's sent over the physical layer to the receiver. At the receiver, the packet moves up the stack, right? The idea is it started at the application layer, and you want to deliver it to the application layer here. And as it goes up the stack, each layer strips off the header or the footer and uses that information to carry out its function. So that's why we say there's a virtual connection between a layer here and a layer here. This layer is writing something for this layer, for the layer on the receiver side to read. Okay, so there's a virtual connection between all the network layers here, and a packet will go through the node with all the functions being executed by the respective layers. The other thing to keep in mind here is that if you look at the endpoints, they implement the entire TCP/IP stack from physical, link, network, transport, application. But the intermediate routers don't. They only implement up to network layer, right? And this is in line with our idea that the internet is an end-to-end network, right? The end-to-end is designed with the end-to-end principle in mind, right? Intelligence is implemented at the endpoints, not at the interior of the network. But we are going to now look at what is happening in the interior of the network. What are these core routers doing? Okay, that's our aim for the next couple of lectures. Okay, so the two key network layer functions, and basically what a router has to do, it has to do forwarding and routing. Okay, routing is the process of determining the next hop, meaning finding the sequence of hops. That's routing. Okay, so routing is to determine the route taken from source to destination. Forwarding is the process of pushing a packet from an input interface to the correct output interface. So for example, a router can have 4 or 5 interfaces. A packet can come in on one interface, and let's say the destination, so let's say a packet comes in on interface 1, but the destination is available on interface 5. So the idea of forwarding a packet from interface 1 to interface 5, or transferring it from interface 1 to 5, is the forwarding problem. Now you might think, why is this hard? It's hard because packets are coming in on all interfaces and need to go to many, on all input interfaces, and need to go out on many output interfaces. So how do you deal with things like collisions and so on, right? So inside every router is a switch, and that switch's job is to do this. And switch design, it turns out, is a huge area. So Cisco invests tons and tons of time and money in switch design, because the faster you can do this forwarding, the faster the router can operate. Okay, this is the limiting thing, the limiting factor for the speed of a router. Okay, so forwarding and routing are the two main functions. We'll see a little bit about how the routing, so there's a forwarding table at a router, and the routing algorithm drives that forwarding table. Okay, so there's an analogy here for the real world, right? Routing is your plan, and forwarding is like getting through the turnstile, figuring out which turnstile to go through to get to. You want to get to the airport. Figuring out which taxi to get into is like forwarding. Routing is I need to get to the airport. Okay? And so the interplay between routing and forwarding. So the forwarding table here is something that says it basically has 2 columns. One column is the destination, the destination, okay, and the second column is the output interface I should forward that packet on if the destination is as in the first column. So for example, if the destination is 0100, then forward on output link 3 or output interface 3. Now what drives this is the routing algorithm, because the routing algorithm says if you need to get to destination 0100, then the next hop is so and so, and that next hop is accessible on output interface 3. It doesn't mean that 0100 is the next hop. Okay, it's like in the network layer header you have the destination IP, right? That's the first column, the destination IP. The second column says the routing algorithm figures out the next hop and says that next hop is available on the second column interface. So here at the first entry here, 0100, its the route to 0100 has a next hop which is accessible on interface 3. Okay? And so that's how the routing algorithm determines the forwarding table. So essentially, you need that's why we say the network layer's job is routing. Okay? Okay? So just, we discussed this idea of circuit switching versus packet switching. The same issues come up when you talk about the network layer. Not surprising, right? Because this is the very first time that you see end-to-end, right? Physical and link don't see end-to-end. So you don't talk about things like statistical multiplexing or packet switching. It's only when you get the network layer and above. And so this question, really comes there. And so packet switching is called a datagram network, okay? And a circuit switching, there's something called a virtual circuit network, okay? And again, it's the same idea behind when we discussed, circuit switching versus packet switching. It's the same set of ideas, okay? So I'm not going to dwell too much on it. Okay, so in a datagram network, it's opportunistic. There's at the network layer. Now, at the transport layer, we actually set up a connection, right? It's connection oriented. There's a 3-way handshake. But network layer, there's no handshaking. It's connectionless. Okay, I just figure out the next hop and I send it. There's no state about the end-to-end connections, even though we are stitching together a set of connections end-to-end, right? We don't keep state about it, and packets are forwarded just using the destination host. So, for example, so you have a node here. The network layer sends data. It will get forwarded by these intermediate routers based on what the end destination is. Okay? So this is our first look at a real forwarding table. So this is it's kind of written strangely, but it's the forwarding table of a router. There are 4 entries here. Okay, 1, 2, 3, and then the otherwise. Okay, and so you see that each entry is a range of addresses, and those range of addresses map to an output interface. Right? So for example, if the address, so if I look at this, so this is a range of addresses. If the destination address is in this range, so this is actually 32 bits here. So this is the binary representation of an IP address. Okay? If the destination address is in this range, the forwarding table says output to interface 0, and so on. If it's here, interface 1, here, interface 2, otherwise, interface 3. So this captures every single destination on the internet, right? 4 entries capture every destination on the internet. Why? Because of the otherwise, right? If it's not any of those, output to interface 3. Now, IP addresses are 32 bits, right? Okay, there are 4 8-byte quantities. So how many binary vectors of length 32 are there? How many binary vectors of length 32 are there? A bit louder? It's 32-bit IP address. Yeah, 2 to the power 32, right? Yes, can everybody count that or not? Can you or not? Come, I need a show of hands. If you know that the number of binary vectors of length n is 2 to the n, please raise your hand. I need to know if I need to explain this or not. I don't want to just gloss over it. Seriously, like I said, if you have never figured this out before, now is the time. Come. Can I ask who doesn't know? I noticed there are a few people who didn't raise their hand to either yes or no. Like, for example, this lady here with the heart on her laptop? Yeah, hi. You didn't raise your hand. Do you know or not? I asked how many binary vectors of length n are there? Do you know? Sorry? Is not clear? No, I can't hear you. You're too soft. I'm sorry. Oh, okay. So, okay, so how many binary vectors of length 2? Can you tell me that? Can I ask how many binary vectors of length 2? Like 0, 0, 0, 1, 1, 0, and 1, 1. So how many binary vectors of length 2? Can you tell me? I'm talking, huh? Yeah, so how many? There's 0, 0, 0, 1, 1, 0, 1, 1. So how many? 4, right? Yeah. If I went to 3, could you count it? If I have length 3, how many? 8, right. So 32, 2 to the power of 32. Does that make sense? Do you kind of see that? Yeah, so if you have binary vectors of length n, they're 2 to the power n. So 32 here, 2 to the 32, if you want to, I mean, I wrote it up there, but how would you do it? 2 to the 10 is what? 1024, right? Then what? If I, what am I doing? 2 to the what? 2 to the 32, right? So 2 to the 10 is 1024. I think 4 billion is right? Then if I square that, that's 10 squared is let me see, 2 to the 10. So 2 to the 20 is about 1 million, right? 2 to the 20 is about 1 million. Then you have to add, so 2 to the, I think you can figure it out. I don't do these things in my head. It's about 4 billion. But actually, you should get good at doing this. It will turn out to be useful. Okay? So the point is, every router has to be able to route to all 4 billion addresses. Okay? So in the worst case, what's the worst case? What's the simplest design for a router? Like, what's the most naive design for a router? For a forwarding table? Are you looking for a trick or something? Chen Hui, you look confused. Oh, naive means simple. As simple as possible. Don't think complicated. If I have 4 billion destinations, how would you design the forwarding table? Yeah, just tell me. No, so how would you design the forwarding table? Yeah.
I get in one and I just send it out.
No, I'm not talking. That depends on network architecture, right? I'm just. How would you design a forwarding table? You would need how many entries? How many entries? What? Yeah, 4 billion entries, and then you would have an interface where the next hop is on for all those 4 billion entries, right? That would make routing tables very inefficient, because I didn't ask you to design a complicated table. I asked you to design a simple scheme. A simple scheme is put all 4 billion entries into a table. Is that complicated?
No, I misunderstood it.
Yeah.
I thought you want the table itself to be more simple.
No? That's why I said naive. Yeah, so that's exactly what naive means. Naive means something that uses very, very simple and easy ideas. Okay, not complicated, advanced ideas. So that's what we have to do. We have to have a 4 billion entry table. In fact, that's how you'd have to build an internet with MAC addresses. Right? Because this is what we discussed before. MAC addresses have no structure. So you'd have to have a forwarding table with all MAC addresses. Okay? But for us, IP, like we're lucky, IP addresses are not flat. IP addresses have a structure. Two IP addresses of two nodes that are close to each other are similar. So IP addresses have a hierarchical structure. That's why I can do things like range. Exactly because of this. All like when I say from here to here, aren't all those similar to each other? Because they're in the same range, right? So I'm going to end by just saying that how do we exploit this structure? We don't actually store ranges, we store prefixes, right? Like if you look at this range here, you will see that this range has a lot of the bits the same. Like for example, these first 8 bits are the same in this entire range. In fact, these first 21 bits are the same. They only differ in the 22nd bit and on, and so on. So what I can do is I can just store the prefix. So instead of storing the range, an equivalent way to store the range is to store the prefix. So that's all I need. So this is the equivalent routing table. I just store 3 prefixes and an otherwise, right? So, and the way we do routing, the way we do forwarding, to decide which interface is to do longest prefix matching. So the destination, the packet comes in, you look at the destination address, and you find the prefix that's the longest match. So we'll end with this, but if the destination address is the one on top here, which interface do I route on? Looking at my forwarding table and the destination address that's shown here, which interface am I going to route on? So 0001, right? And then 0. So 0001 and then 0. So notice that interfaces 1 and 2 have a 1 in the 21st bit, right? This one has a 0 in the 21st bit. So it matches which interface? 0. So I'll put this on interface 0. How about the second one? Where I see 1. So I've got to find the longest prefix match. So what's the longest prefix match here? Yeah, interface 1. Right? Even though interface 2 matches 0011, interface 1 matches more. So this gives me the flexibility to route in a rich function, like in a variety of ways. This doesn't constrain me in how I route, what ranges of addresses I route. Right? By doing longest prefix matching, I can have very complex routing or forwarding scenarios. Okay? So let's end here. Okay? When we pick up next time, we'll continue talking about network layer, some of the general ideas. We'll talk about some of the functions implemented at network layer, and eventually get to routing algorithms, which is our main goal. Okay? Thanks. I'll see you on Wednesday.